All right, in the last segment what we did is we derived the equation for the log mean temperature difference. And so what we're going to do now, we're going to take a look at how the temperature is actually within the exchanger. And remember, we're looking at parallel flow double pipe exchanger, how the temperature is mapped to LMTD. And just to write out the expression that we had. And so that's the expression. Now, one thing to note, and this is a bit of a shortcut, or not a shortcut, but it makes it a little easier to remember. And notice that this expression here, TH2 minus TC2, is the one that is in the numerator, and then TH1 minus TC1 is in the denominator. So that is always the way that we have it configured for the LMTD temperature. And so it's useful if you remember those. It makes it a little easier when you're doing your calculations. But what we're now going to do is we're going to go back and really this was in the derivation, but I'm going to summarize it again and figure out what these temperatures are and how they map to where we are in the exchanger. So if we're dealing with a parallel flow heat exchanger, what we have is this is T hot 1 and this is T hot 2, and this is T cold 1 and T cold 2. So that is the way that we designate the temperatures for a parallel flow double pipe. Now looking at counterflow, so if we're looking at a counterflow heat exchanger, then we would have TH1 here, TH2 there, and T cold 1 here, and T cold 2 there. So you can see that what we're doing, we're putting this as being location 1, and this is location 2. Again here, that is location 1, location 2, and then the temperatures would either be hot or cold, and they would correspond. And so that's how you can get the temperatures that you would use within the LMTD expression as shown above. Now, this was derived for a double pipe heat exchanger, and so we do have to make a minor correction if we want to apply it to heat exchangers other than double pipe. Okay, so if we're trying to apply LMTD to something other than a double pipe configuration, then what we would do, we would write out our heat transfer, overall heat transfer coefficient, the area that the overall heat transfer coefficient is computed for, this correction factor F, and then delta Tm. And F is a correction factor. And delta Tm is the log mean temperature difference for counterflow double pipe. So essentially what we're doing is we're mapping one to the other. Now where do you get F from? F is from figures. I'm not going to give you any of them. You would find those in any textbook. But you would have them for cross-flow heat exchangers, so radiators, things like that. You'd also have them for shell and tube heat exchangers. You could find the value of F, and those would be tabulated in these figures, and you would look up the value from that. So what we're going to do in the next segment, we're going to solve some problems using the LMTD, and we'll see how it works. So that's where we're going.